Hello, we're doing business applications 4-14. I'm currently on problem number 2. A management company is going to build a new apartment complex. They know that if the complex contains X apartments, the maintenance costs for the building, landscaping, etc. will be C of X equals 4,000 plus 14x minus 0.04x squared. So we have a negative quadratic equation. I'm guessing it's going to be concave down. And they're asking us how many apartments should the complex have in order to minimize the maintenance cost. So this is a cost equation, and we're asked to minimize this, but the graph is going to be concave down. So it looks like we don't have a relative min, we have a relative max, and wherever the lowest point on our graph is, that's going to be the absolute min. So this problem, we're going to be looking for the absolute min. I will find where the derivative equals 0, but that's not going to be the answer this time. So what you should figure out are your parameters. It says that the land they have purchased can hold at most 500 apartments. So that's going to be your upper limit. And your lower limit, of course, would be 0. So those are going to be my extreme values, 0 and 500. And then I'm going to find my relative max or min point. So I'm going to take the first derivative, set it equal to 0. Find x, I get 175. If I take the second derivative, I do confirm that as concave down. So this 175 is actually a relative max. So this will actually be more expensive, more costly for them just to build 175 apartments. So then what I do is I plug in 500 into the original equation to see how much money that will cost, and that only cost $1,000 in maintenance cost. I believe this is per unit. And then the 175, the most expensive, was $5,225 per unit. So 500 is my absolute min, so that is the minimum that we want. So that is the answer. So when 500 apartments are built, then that's going to minimize the maintenance cost at $1,000 . Okay, on to the next problem, number 3. We have another production cost problem, and of course they're going to use the generic widgets again. And we have a cost equation. This time we have an x cubed equation, so we have the possibility of having a relative max and a relative min, and probably inflection points in here. They don't ask us to find the relative max or the relative min. They just ask us what are the marginal costs when x equals 175 and when x equals 300. So I made a little mistake the first time. I might have plugged this into the original equation instead of plugging it into the derivative equation. So make sure you find the derivative. The derivative is the marginal cost. So your marginal cost is 6 minus 0.08x plus 0.0009x squared. So I'm going to set that, I would set that equal to 0 to find the relative max and min points, but they only ask us to find the marginal cost at 175 and 300. So I plug in 175, it's 19.56. What does that number mean? That means the cost to produce one item, one widget, around 175 is approximately 19.56. And I say approximately because right at 175, that's the marginal cost, but as you go up, the costs are changing. The marginal costs are changing every time you go up a fraction. So the answer key said for the 176th widget, it would cost about $19.56 to produce. So any additional or the change in cost between each widget would be about 19.56, around 175 widgets. And plug in 300. So the cost around 300 widgets, so from 300 to 301 would be about $63. And the only reason I say about is because it's constantly changing. So much more expensive to produce 300 plus widgets, it looks like, than to produce 175. And that is the answer for number 3. That means trouble scrolling down here. Yep. Problem number 4, the production cost in dollars per month of producing X widgets is given by C of X 200 plus 0.5X plus 10,000 divided by X. When I first copied this problem over, I only used 1,000 instead of 10,000. So I had to go through and change everything. So my original answers were off because I used 1,000 instead of 10,000. So the original problem is 10,000 over X. So what are the marginal costs when X equals 200, when X equals 500? So the marginal cost is the change in cost at those points. So I'm going to find the first derivative. I did find the second derivative, but that's only necessary if you want to figure out if it's concave up, concave down, or inflection points. We do not need to do any of that, so you do not need to find the second derivative. So just find the first derivative. Plug in 200. So around approximately 200 to 201, there's an additional 25-cent cost to produce the extra widget. On the other hand, when you're at 500 widgets, to produce an additional widget up to 501 would cost 46 cents. So it costs more at the higher number here. And that's all he has asked you to do, so that's all you have to do. So now we're going on to the next problem. The next set here is the application problems. This is review for the test. This test isn't very substantial, very long. I have an application of velocity and acceleration. So the original equation is distance versus time. And this is used all the time in physics. Sometimes your letters are different, but it's basically the same thing. So this is your distance versus time quadratic equation. Tells you how far away, well, this is just height, so how far up and down something is going. In physics, sometimes they do two different sets of equations, up, down, and horizontal. This is only vertical. So you can pretend like it's being shot straight up in the air or it's being shot out. It doesn't matter. We're just measuring how high this object is going and then how low it's going. So obviously anytime we get a negative value, it's going down, positive's going up. If your position's below 0, then that's below the quote-unquote ground, and anything above that is obviously high. And we're also not going to do any negative time, so the time will be a minimum at 0. We will not go to the left of 0. So here's the original quadratic equation. To find the velocity is the change in feet per change in seconds, the change in distance over change in time. So that is just the first derivative. So if I find the first derivative, I get negative 32t plus 45. And we want to find the velocity at 2 seconds. So plug in 2, and I get negative 19 feet per second. The negative just means that is going downward. So if you were to plug in 1, that would still be going up between 0 and 1 second. If you want to find the exact peak, you'd set this derivative equal to 0. So that's going to be a decimal, 1 point something. So between 0 and that 1 point something, it's going up. It hits a max, and then it's going down. Of course, everything you throw in the air, due to gravity, is going to come back down. In physics, they usually deal with 9.8 meters per second squared, and you would plug in this formula, you'd use 4.9 meters per second, or 4.9 t squared would be the gravitational constant. Here, we'll talk about a little bit later. The next problem, part B, acceleration. You take the second derivative and it's negative 32. So what does that mean? That is the force acting on it, acceleration due to gravity. So the acceleration due to gravity in feet per second is negative 32 feet per second squared. So that's how much the velocity is changing every second. So at 1 second, it's negative 32 feet per second squared. At 2 seconds, it's the same thing. No matter what you plug in, there's no variable here. It's always going to be negative 32 feet per second squared because gravity is a constant. So the acceleration due to gravity will always be the same, negative 32 feet per second. Find the highest position reach. Again, you are going to take that derivative and set it equal to 0. You do get a decimal, and it's 1.4. So between 0 and 1.4, you have a positive velocity. It's going up. It's going to be getting smaller numbers. I think as 0, it's going to be closer to 45 feet per second. And then it's decreasing. So again, to find the relative max or min points for this whole chapter, you're going to find the derivative, first derivative, and set it equal to 0. This answer is, the time is approximately 1.4 seconds. If you plug that into the original position function, the height at approximately 1.4 seconds is about 36.6 feet. If you take the second derivative just to verify, again, the second derivative test tells you if you've concave up, concave down. It's negative, so it's concave down, so this must be a relative max. Next, we are going to continue to review for the test using the sheets. This is the only review I have for this. I might look around in case I think I need to review any more. but this will be it. And I will do one more